So, yeah, we are live, and in the very beginning, Sebastian, I want to ask you to introduce yourself and John and Heinz. And before we start, I want to say that it's a great honor for us to have you on board this year. Thank you for making this talk. And gentlemen, the broadcast is yours.
So hello, всем привет, and I'm very happy to be here. My name is Sebastian. I work for this company called IBM, and I do things with Java. And I'm very, very happy to introduce two very nice people that will tell you things about Java. So first of all, Heinz Kabutz, who you probably know and should know all things Java. So he has a newsletter with an incredible amount of subscribers. And you probably know him. He tries to encourage people on Twitter to run a little bit more, and he's getting everybody jealous about pictures, nice pictures on the island of Crete where he lives. And he's also the mastermind behind probably the most famous Java-conference, JCrete, that happens on the island of Crete. And of course, he's an expert on all things concurrency with Java, so you should definitely check out his content and his video courses. And also the second person, Mr. John Green, who is a lifelong learner, polyglot, and lover of mathematics. I was happy to meet him on this JCrete conference as well. And also, of course, he's an expert in all things concurrency with Java. And I'm very, very happy to meet both of them now virtually. And I hope you all are already looking forward to really hardcore content on Java. So, gentlemen, welcome. How are you doing?
Thank you, Sebastian.
Thanks so much, Sebastian. I'm doing great. Doing great over in Crete. Yeah,
as you can see,
my first time.
That all being said today, which is absolutely wonderful.
Sunshine in England? That's strange.
Yes, very strange.
Awesome. All right, then I would say without any further words or further introduction, Heinz, what do you have for us today? I think we're now about to start the presentation. The stage is yours.
Thanks. And I do want to just say a special word of thanks to Alexei and all the people who've invited me. I think Ivan also invited me quite a few times to come to JokerConf, and it just never worked out. November's normally very, very busy on my traveling, and I just never managed to get to JokerConf. So I'm really thrilled to be at least virtually in St. Petersburg, and I hope to do this in real life, in person, one of these days in the future. So that'll be great. So thanks for inviting me. And so John and I have been working together for a long time. For 30 years, we've been working together. We studied together, and we've done lots of research together on concurrency as well. We've been playing around with Project Loom, spinning up a server with 2 million threads, pinging backwards and forwards between servers and clients. And so we've had lots of fun together. And John is going to be the live audience that I need for a talk. So he's going to interrupt with questions at some point. Questions which you might want to ask, but be too shy to ask. That's what he's going to mainly be doing. So I'm going to be doing a lot of the talking. But John will interrupt with some hopefully very good questions. Hopefully they won't be too hard. Hopefully I'll be able to answer them. But I know that John knows the answer when he asks the question. So at least if I don't know the answer, I can say, that's a great question, John. What do you think? All right. So
if you think back to the origins of the Joker in the court, the Joker was the person who the king would have to tell him when there was something that other people might get their heads chopped off if they told him. So we thought, since it's JokerConf, why not have a Joker?
So you're the Joker and I'm the king. Or I think it's the other way around. I think I'm the Joker and you're the king. There we go. Don't chop off my head. Right, let's have some fun. So I've got this newsletter, the tweet. On my Twitter, I mostly tweet nonsense. So don't follow me if you want some useful information. But also, sometimes I tweet things like puzzles. Here's a little question. Which of these mechanisms of waiting is compatible with fibers in Project Loom? Project Loom, of course, now it's called virtual threads, but it used to be called fibers. And what I find interesting about this question, I thought the answer would be completely obvious, right? the correct answer is thread.sleep. But it turns out that only 18% of my followers, I think they're following me for pictures of Crete and running, actually got that one right, which is not that great. You know, people were quite happy to do on spin weight and wait and for and infinite loops inside virtual threads, which of course won't get you very far. So yeah. Now there are three sections we're going to look at. The first one is called the phaser, and phaser is a class which was added in Java 7. It allows threads to coordinate with each other. So if you want to go through several phases, right, that's where the name comes from, you can use this. So coordination. Let's say you want to have all threads starting something at the same time. Like we have at the moment I've got this this show where every morning at 8 o'clock UTC, which is 10 o'clock Eastern European time, we have a meetup for 8 minutes. So just 8 minutes really fast. And it's important that we all start at the same time. So we have a phaser, and the phaser starts at the same time. And you might know CountDownLatch, and you might have heard of CyclicBarrier. Those are classes that were added in Java 1.5. And CountDownLatch is basically a countdown. 10, 9, 8, 7, 6, 4, 5, 1, 0, start, right? I skipped a few there. And CyclicBarrier is one where you all do something at the same time. But the problem with CountDownLatch is that you can't reset it. So once you're at 0, that's it. It's open. It can never get reset. And you can't reuse it, in other words. And with CyclicBarrier, you can't change the parties. So CyclicBarrier could be like your daily Scrum meeting, right? Daily Scrum. You're getting together. But the problem with the CyclicBarrier is if one of them doesn't show up and you have a timeout, you broke the barrier, then you have to reset the barrier to be able to use it again. And and you can't change the parties as you go along. So it's not very flexible. And another problem you have with the CountDownLatch and the CyclicBarrier is that the way that they handle interrupted exception is a bit old-fashioned, right? A bit old-fashioned. So not that great, but they do work and people do use them. So with the phaser, this is a Java 7 class. So that's, of course, old by now, but not many people know it. And it's one of those classes that is easy to use, but a little bit tricky to understand, whereas CountDownLatch is easy to understand, but more tricky to use. So we can change the number of parties over time. It's got a more modern way of managing interrupted exceptions, which is great. And so the parties is a bit like the count in CountDownLatch and parties in CyclicBarrier. The other thing which used to make this one unique is that it is a managed blocker as well, which means you can use the phaser inside a fork join pool. Now, I'm assuming because we're all, we had Java-conf, which is a conference which I've heard only good things about. Because we had Java-conf, I'm assuming that you're all using very new versions of Java. Java 11 upwards, maybe Java 15 or 16. I'm using Java 16 early edition. So things have changed a bit with managed blocker, and I'll mention that a bit later. But in the early versions, the only class that actually was a managed blocker was phaser. We'll get back to that in a bit. But I want to show a demo of what I call co-joining approaches. And co-joining, what I want to do is I want to have a bunch of threads that start work at the same time. Now, this is just a fun experiment. It's maybe of not much practical use, but sometimes I do these things and people say, I really wanted something like that, right? I want them to start at the same time. And so there are different ways you can do it, and I'll show you the demo in a moment. There's a GitHub repository there and branches Java-conf. And so with this demo, I'm going to have different ways that we want to get the thread starting at the same time. Now, of course, I'm busy doing a broadcast, so I'm not going to do it on my machine. I'm going to do it on my server, and every step that I do in my code, I'm going to check in and then run on the server. So it's going to be check in, run, check in, run, check in, run. And I'm going to use different approaches for the co-joining. The one will be wait, notify. then Re-Entrant Lock, then CountDownLatch, phaser. And we will see the purpose of this demo is to try out which approach for getting everybody to start at the same time gets them to start closest together, right? And you would probably think that this shouldn't matter because, well, why would it matter? But it actually is, there's a difference. Let's try it out. I'll sit down because I'm not Venkat. I do code standing up, but not when I'm busy doing a webinar. Don't have the technology here. So let's zoom in a bit and have a look at the code. All right, and let's go over to IntelliJ. And so I've got a little demo code here. I've got my, what is it? First of all, the code joining task tester. And you need at least 4 cores for this test. If you have less than 4 cores, it's not going to work. And then I've got a code joining task. It remembers the start time as nano time. And then what we are going to do is to find out how close together did they all start, right? So we're going to have a joiner.run. Joiner.run is just a runnable, which will wait until everybody's there at the same place, and then the actual task will be run afterwards. The run's going to be boring. It's going to be just an empty task. What we are interested in is the start time. How close together do these tasks all begin? That's what we're trying to figure out. So let's try this out. We're going to have our
So Heinz,
the first
before
one
you
will
start
be
on that,
before I start.
Before you start, let me see if I understand the picture. We've got something like a race, isn't it? It's imagine we're at the Olympics watching the 100-meter race, and we have a number of lanes, one for each core in our CPU. But unfortunately, one of those lanes has the guy with a starting gun in his hand, so we have to leave one free for him to blast his gun, and then they all have to wait until he starts. That's what you're doing, right? Yeah,
sort of like that. So you've got one thread on the side, one thread on the side, and that thread on the side will be the thread which will fire the starting gun. And we're going to have, I think we're going to have the number of threads will be, I think 4, which will be, in fact, it's going to be, it's going to be 2 threads less than the number of cores. So I've got 6 cores on my server. I'm going to have 4 threads which are in the lanes waiting to run. And all we're interested in is the first microsecond after we shoot the gun. So this is a really good analogy. Thanks, John. So the referee is standing with the gun, he shoots the gun, and from when he shoots, how long does it take for those threads to all get going, right? To all start, right? So that's a really good analogy. And the first one will be we do nothing. In other words, we just randomly let the operating system do what they do, scheduling the threads, and we just hope for the best. So there's no coordination between the threads to see who's going to really start first. So none joiner is just doing nothing. So there's no waiting, there's no signaling, we just hope for the best. The next one we'll do is a wait notify co-joiner. So here we're going to do something like this. We're going to have a private Boolean ready, which starts as false. We're going to make the 2 methods to be synchronized. Synchronized run waiter, synchronized run signaler. The run waiter will say, while not ready, we wait, and then we carry on going. And the run signaler will say ready equals true, and then we're going to say notify all. So it's like, that's the starting gun saying start running. And what we're doing is coming in and seeing how long does it take from when the gun goes off until those athletes have gotten off the starting blocks and are running. That's exactly what we're trying to find out here. Oops, now you see here there's a compiler error, underlined wait. And the problem here is that we need to worry about the interrupted exception. So what we really want to do is to ignore that whilst we're waiting. We actually want to do a wait uninterruptibly. But there is no such method in Java, at least with made notify. So we need to do some more work with it. And we need to do something like that. Probably what we'll do is before we start, we're going to say Boolean interrupted equals thread.interrupted. So we get the current status of interrupted and we set it into that Boolean and we reset the state at the same time. If anybody interrupts whilst we're waiting, we're just going to say interrupted equals true and keep on waiting. And once we exit from here, we're going to say, okay, we were interrupted. So if we were interrupted, we're going to say thread.current thread.interrupt. We basically do a self interrupt over here. So interrupting ourselves. Right?
Heinz,
so
I have a question
let's have a look. And
I'm pretty sure that our university professor said we should keep that critical section as short as possible. Is it important in this case?
okay.
Because we're synchronizing the whole method and we have all sorts of things going there. How little can we synchronize? How little can we get away with if we don't want to synchronize all the code in the run waiter?
Well, when you do wait, what happens is the first thing you do is you let go of the lock. That's what wait does. So
Yeah.
that allows another thread to come into the run signaler and call notify all.
Right.
So you don't actually hold the lock the whole time. When wait happens, one of the first things, not exactly the first thing, but the second thing that happens is that the wait lets go of the lock. So you allowed others to go in as well.
Oh, that's brilliant.
So what we're going to do is we're going to just try these two first. So I'm going to listen, and what I'll do, this is in the Joker-conf branch. I'm just going to have all the messages being one. Otherwise, it's going to take too long to. In fact, I might not do that. I'll change my mind in a moment. So here we're running, and I've got my little code. I'm going to run the phaser code joiner, which is going to compile and run that test. Now it's going along, doing all this, and what you'll notice is that there are two things which I'm measuring. I'm measuring the maximum difference in nanoseconds between the first thread that starts running and the last thread that starts running. Now, this is all on a single socket, so it's not, we don't have the problem with having multiple sockets and getting different nanotimes, so it's all on one socket. But you can see there's a difference of about 180 microseconds between the first, and if I don't do anything, over time, sort of the best we have here is 12 microseconds between the two. Whereas if you look at the wait notify, that is actually not doing that much better than doing nothing, right? In fact, it seems to be worse than doing nothing at all. So the jobs are starting further apart from each other because, of course, when you get the notify, you all have to get the lock, right? You have to get the lock, and then you can move forward. So if you introduced a bottleneck where there wasn't a bottleneck before. The first thing that you see is the max. That's the number. The second thing is the total. That is, if I add up all the differences between all the threads and all the runs, and a big number means that we always started quite far apart, right? Quite far apart, and 150 milliseconds in total apart with all my runs in those 3 seconds. So each run, I think, is 3 seconds or a second or so. Let's try doing this a bit differently. So this was the wait notify. Let's try do it with Re-Entrant Lock. So private final lock equals new Re-Entrant Lock. And we also need a condition for that. So it's going to be wait until ready condition equals lock.new condition. And I'm also going to have a private Boolean, again, ready, which starts as false and later on becomes true. So here we're going to, again, have something similar. We're going to have while not ready, and this time we can actually wait on that condition uninterruptedly. We can say await uninterruptedly, like that. And so I don't have to do try catch. This does the saving for interrupt until later for me. So this is a little bit easier to use. And of course, I need to put a lock around it, which is a bit uglier than the other one. So lock.lock, while not ready, ready condition await uninterruptedly. And then in the signaler, the starting gun, we're going to say ready equals true, and ready condition dot signal all that we can start running. And again, we need to put a lock around that too. So I've got three different approaches. One is do nothing. The second one is do await notify. And the third one is to do a lock and condition. Now, I'll need to point out something quickly, and that is that the condition await is compatible with virtual threads in Project Loom at the moment, whereas the wait is not. So if you wait on a virtual thread in Project Loom, that carrier thread is going to get suspended, and you won't be able to use that thread for other virtual threads. So that's going to cause a problem. But apparently that's going to get solved sometime in the future. We'll see when, I'm not sure when. But once it's solved, then that problem will of course go away. So John, I think
that's
we'll
good
add
news.
that in as well.
I'm glad we'll be able to use wait and notify again.
Yeah, except we probably shouldn't be using wait notify to begin with, but if we are, at least we can move our old code through to Project Loom. And the funny thing with Project Loom is we actually, what we found is when we started working with it, normally when you make threads, you know that you can make maybe a couple of thousand threads, but all of a sudden you can make, 30 million threads, and it changes everything, because things which in the past didn't really make a difference, like which collection am I going to use, ArrayList or whatever, who cares, right? Use kind of a few thousand of those, doesn't matter. All of a sudden, you've got like 32 million of them, and it starts to make a really big difference. Let's run it again and see what happens here. So this is now with the condition as well, running on my server, and you can see that the condition doesn't really do much better than wait notify. It's about the same. The total is roughly the same. Of course, it'll vary, but this is all random here. So, but it's in the same direction. None sometimes does much worse, and sometimes does better. But none is just, I'm not doing any coordination at all. Let's look at the count work. Here I'm going to say a private final countdown latch, and I can do it in one of two ways. The one way to do is to say that every waiter will have to call countdown just to like a roll call. I'm here, and then that thread can go and wait. So that's one way. The other one is to have a single countdown latch for everybody. So I'm going to do it with the first approach. We're going to say latch equals new countdown latch. The number of parties we can get from the constants, that is the parties plus 1. It's going to be plus 1 over here. And then inside the waiter, we're going to say latch dot countdown first, and then latch dot await to wait. And again, we've got the same problem as before, that we have to worry about the interrupted exception. We need to have a mechanism to deal with that. Interrupted equals thread dot interrupted, and then we're going to put a loop in here while true, latch await, and then if we get interrupted, we're just going to say interrupted equals true, and once we successfully complete latch await, we're going to say if interrupted thread.current thread, so we don't lose that information, and then return from there. That's our run waiter, nice and easy. And our run signaler is going to be super easy. We're just going to say latch.countdown. This is going to give us nice coordination. Unfortunately, the code is still kind of ugly, but it's mostly ugly because of the interrupted exception. I told you the mechanism is not that great. So if we now run that, try it out. Let's put that in. CountDownLatch, and push that, and then hopefully we should be able to run that with the CountDownLatch there as well. And as I said, this is all in my GitHub repository, so you're welcome to try it out yourself as well. And you'll see that it is not, oh, we're not running it, so there's a problem. Why is it not running? Oh, because I was too quick. That's why it was not running it. So we can see that the CountDownLatch is actually not better. It seems even worse than the other mechanisms. All right. Okay, great. So we're walking one step forward and two steps backwards. How annoying is that? Okay, then the next one is the volatile spin cojoiner. Here we just have the threads, because I've got enough cores. They're just sitting doing nothing. So we might as well just put them to some use. We're going to make a private volatile Boolean ready equals false. And the waiters will simply say while not ready. And to be good citizens, we'll say thread.onSpinWait. So, and then the run signaler will simply say ready equals true. Then spin until eventually we become ready, and then we can move on. And if you run this test,
I always make mistakes with that one, Heinz. I always forget to put volatile in, or I forget to take the synchronized off. Two things that I
know you don't
check off on my checklist.
You don't really do that, otherwise you wouldn't be in the call. But yes, it's very important to make it volatile. If you don't make it volatile, then you're going to have then what will happen is this one might cache that information and not actually read the value in the future.
Yeah. And don't make it synchronized as well, or you'll just be wasting time.
Yeah, exactly. If you make it synchronized, then no one else can get in there. That's an even more fun one. And you'll have one thread just spinning loops, the other one not being able to get much progress. All right, let's try that. And yeah, it's managed to get the latest changes. And we actually see that the volatile spin cojoiner is even better at getting this right. You can see the total is consistently the best of all of them. Now, we did try using acquire release. It actually has the same characteristics, at least on the hardware we tried. But let's try the phaser. That's what we've all come here for. Now, what I want to focus on is how much easier it is to code this. That's what I want to focus on, because that's really the important part. There are lots of options, but it's easy to use once you know which ones to use. So phaser equals new phase. Again, we're going to have the number of parties, which is going to get from the constants dot parties plus 1. And then for the waiter, we want to wait. So we can say phaser dot, which one to use? We can have arrive, await. Which one to use? Well, the one that we want to use here is arrive and await advance. This is a little bit like the latch countdown and await combined. It's like saying, I'm here, and I'm waiting for everyone else to get here before we can start. You can see I don't have to worry about interrupted exceptions. If the thread gets interrupted, that status will get saved until later, just like I've had to do manually in my CountDownLatch, in my wait notify. Here it gets done for me. So that's great. Where's my phaser? There's my phaser. And the signaler will say phaser dot arrive and deregister. And why would it do that? John, why would it deregister there? What do you think?
Well, I was wondering about that, because how many races are we running here? Because each of these phases is only being used once for one of the races. But if we had to use the same phaser over and over again, we might have had a problem with the deregistration.
Exactly.
Because
so
we would no longer wait for the gunman to arrive.
Right. So what we're doing is we're saying, if we wanted to, we could actually have coordinated starts over and over again. So we start all together, right? And what the run signaler would do is it would fire the first gun and then step aside. And then after that, whenever everybody arrives back at the starting, they just go again. But they wait for everybody else to come to the same place, and then they begin. Wouldn't that make for a really fun Olympic race? You have to run 400 meters once around the field, but you can't do the second round until everybody's back, right? Then you can go to the second round and see who falls over first, right? From exhaustion.
Well, I guess the runners are quite professional, so they're all going to wait for each other, I guess, on the second round. They're all professionals,
exactly,
right?
exactly. More professionals, exactly right. So let's try that out. Let's do the phaser. Let's do that co-joiner. I'll just check that in, and we'll see how that performs. Now, the focus is how easy it is to write the code. Don't worry about the performance, doesn't matter, right? However, you see that the phaser has better coordination by far. It even beats the volatile spin, which I am very surprised. So you can see sort of the three microseconds difference between the first and the last, and look at that. We've got 8 million in total. Now you can look at the code, you can download it and have a look and play with it. But that's the experiment, which I thought was quite interesting. Right, now, one question which John wanted to ask me, but which he didn't yet. What do you want to ask about numbers of parties, John?
Yes, I was thinking about all those millions of threads we can have with Loom, Heinz, and I want to get my hands on a supercomputer and start this experiment with, I don't know, 1 million cores? Can we do that? Can we use a phaser to coordinate 1 million of these cores?
Loom is you don't need 1 million cores, right? You just need 6 cores, and you can have 2 million threads yes. running on those 6 cores, right? So what happens if you do that? Now, when phaser was written, was Java 7, and in Java 7, at that time, we didn't really have machines that could cope with that many native threads, because each Java thread was linked to a native thread. And so the phaser is actually limited to 65,000 parties. So, 2 to the power of 16 number of parties. And unfortunately, that's a limitation. You don't have the same limitation with CountDownLatch. You've got, integer.max value of maximum. But what they did was they made it possible to tier phasers, to build them up in a hierarchy. And the purpose of this is to reduce contention. But it is a bit of you can use the same mechanism to also increase the number of parties. Okay? And it looks like this. So I've got here a phaser, a root with a new phase of size 3. And then I make a child phaser with the root phaser as its root, comma 4. And then C2 is new phaser root, comma 5, and C3 is new phaser C2, comma 0. So when you print out all the different values, you can see that, for example, C3 was constructed with C2 as a root, but it doesn't have any phases itself, any parties itself. This one will have 0 being printed out as numbers of parties, 0 as number of parties. Whereas C2 has got 5, and the reason it's got 5 is because itself has 5, but the children it contains have none, which is why it stays at 5. C1 doesn't have any children, so it stays at 4, but root will have its own parties, as 1 for each child phaser that has at least 1 party. So you end up with the root phaser having 5 parties. You say 3, but actually it has C1 and C2 as direct children, and so it uses those as well. And so here's your root with 3. You create C1 as a child of root, and so the parties in the root increases to 4. We then make C2 with parties equals 3, so that bumps it up to 5. If I make C2 with 0 parties, that does not increase the parties in C2. Now, of course, you can increase the number of parties over time. So that, of course, would then affect everything. And if you really want to make a phaser with, you know, 1 million threads coordinating, you can do it. I've done it. I don't really recommend it, but you can do it by building up a tree of phasers. I mentioned early on that we've got a managed blocker, or the managed blocker is a mechanism that is used, and they use that in order to keep the parallelism high within a fork join pool. So when you make a fork join pool, you don't specify the maximum number of threads. Generally, you can, but it's normally not done. You specify what's your desired parallelism. So if I've got 6 cores and 12 hyperthreads, hardware threads, I might want my parallel, or 6, depends on what I want, or 4, or 1. But I can decide how many threads I want running at the same time. And what the managed blocker says, it says that if a construct is blocking a thread, if it's blocking a thread, then what that will do is it might create additional threads inside your fork join pool to keep your parallelism at that level that you specified. So if one thread starts blocking, that's okay. Other threads are made to keep the parallelism high. There's a limit as to how far they go, but they will try and keep the parallelism at what you wanted. And in Java 7, you only had the phaser. Java 8, they also added the completable future. Java 9, they've got process and submission publisher. And then Java 14, they also changed the abstract queued synchronizer, which is really cool because that's used for Re-Entrant Lock, Re-Entrant Read-Write Lock, CountDownLatch and Semaphore. All of those use the same thing. And then in Project Loom, they have also added link transfer queue, synchronous queue, and select the impl. So this is a very interesting little piece of technology to keep the parallelism high. Oh, by the way, I mentioned before we've got this little JGym, and it's 8 minutes of Java micro lesson. It's not recorded, so you got to come there live. We've got quite a few people coming. It's hundreds of people coming every morning for 8 minutes, and we have a lot of fun. Just one short lesson, 8 minutes. And there's just a link for you to sign up if you're interested. All right. So the next part I want to talk about is StampedLock, and I think I'll stand for that one again to get me some extra oxygen because the oxygen's high up. My son is opening the window. Luckily, it's not minus 25 here, like in St. Petersburg. So, what is StampedLock? StampedLock is a Java 8 synchronizer that allows us to do optimistic reads. If you look at Re-Entrant Read-Write Lock, for example, that can do pessimistic writes and pessimistic reads, but it can't do optimistic reading. StampedLock is not a re-entrant lock. Now, re-entrant is actually quite useful, but for this it wouldn't work. And we use StampedLock when we've got multiple fields and we're trying to enforce an invariant across these multiple fields. For simple classes, just with art invariance as a single field, synchronize and volatile is normally going to be easier to code and actually faster. And the idioms for StampedLock are a little bit tricky to get right. So I always look at the idiom when I code it. I don't code it out of my head. I always look at how to do it because I don't want to make a mistake. If you make a mistake, it can get you can get problems. It can become very slow, and you can get mistakes in your code. And finally,
where can we find these idioms?
Quite difficult as well. The idioms you'll find in the Java docs. So if you look at the Java doc for StampedLock, there's an idiom for each different type of thing you might want to do. And then you need to simply apply that to you. But there are a few catches because you need to be very careful when you're doing an optimistic read, because whilst you're reading, somebody else might be writing to the same to the same object. And this means that you might be doing dirty reads. You need to be very careful that you don't cause exceptions whilst doing that reading. For example, if you're reading a data structure that changes whilst you're reading, you don't want that to cause problems. Stamped lock, whenever you do lock, it returns a number, and we use that same number to also unlock again afterwards. So that's what the stamped lock does, and this means the stamped lock doesn't know who has the lock. Who has the lock? It just hands out the stamp, and then you use that same number to unlock it again later. And that also means you can split locking and unlocking between threads. The first type of lock is the pessimistic exclusive lock. That's the right lock. So the pessimistic exclusive lock. That's like your synchronized, right? Or your re-entrant lock. And the way you do it is you call right lock. That returns a number. The number will never be 0. It's always going to be a stamp. And you use the same number to unlock later. So you can say right lock and then unlock right. There are a bunch of other methods like lock with a timeout, try lock, with a timeout, and so on. But and there's also one which is try convert to right lock. So if you've got a read lock, you can try to convert to right lock. It might work or it might not work. If you try that with a re-entrant read right lock, if you try and convert to a right lock from read lock, it won't work. It'll get a deadlock. But here it will try to do it. If it works, you get back a 0. Otherwise, you will simply have to, otherwise you get it. So 0 means you were not successful. All right, I wrote about this in a newsletter a few months ago. All right, the pessimistic non-exclusive read is a little bit like your re-entrant read right lock, read lock. So you say read lock, get a number back again. Again, it can't be 0, it will block until it gets the lock. So it will get blocked if another thread currently holds the right lock. And otherwise, it gets it back. You can have lots of threads at the same time getting a read lock. And you can also try convert something else to read lock. You can unlock read, and you can call unlock in general, which will unlock either read or write. So far, this is maybe better than re-entrant read write lock. There are some maybe performance benefits, but it's very similar to re-entrant read write lock. And now comes the really cool one, which is the optimistic non-exclusive read. There's no lock as such, because, well, you're not stopping anybody else. I'm not stopping another thread from making forward progress. And the try-optimistic read will try to get an optimistic read stamp. Now, it might return 0 if a write stamp has been issued at that point. So if somebody's busy writing and you say, give me an optimistic read, you'll get back a 0. Even if the data, even if the fields are not dirty, it will still come back with 0. But we're going to assume it's not 0 and move on. The validate will return true if the stamp was non-zero and no write lock has been requested in the meantime, since we called try-optimistic read. Now you can see we get the stamp, we call validate. You want to do as little as possible between these 2 points to increase your chances of winning the race and not having to reread the data. So here's the idiom that we normally use for optimistic read. Well, normally, that's what I normally use. There's a newer one, which is in Java 11. This is from Java 8. There's a Java 11 one, which I'll show you in a bit. And I will show you what parts are better with the new one. I want to explain how this one works. The newer one is similar. It's got the same principles, but there are some small differences. The first thing is we try get an optimistic read. And we assume it's not 0. 0 would mean somebody else currently has a write lock. We then read the fields into local variables. So I've read the fields into local variables. And then we say if not sl.validate stamp. So if not sl.validate stamp, if somebody else in the meantime has asked for write lock, we need to assume that the state is dirty, and we need to reread it again. And of course, here you could put in a loop and try 3-4 times before you give up, or you could leave it like this. And then we do stamp sl.readLock. And so if validator is false, we're going to reread the state into local variables. Okay, and we're doing it with a pessimistic read. So if somebody else currently has a write lock, we will simply stand back and wait a bit until they're done, and then we'll read the state into local state, and then we'll use that state afterwards for whatever processing we're using. Now, there's something about this idiom which I don't like so much, and that is that I've got two places where I'm reading the values from the fields into local variables. Two different places. So if I change the values, I've got, so it's not so nice, but it's the other new idiom will improve that. Now, Sebastian mentioned earlier on that I live in Greece on the island of Crete, where we do this wonderful conference, unconference, and we had a crocodile, like a live, real crocodile walking around the island. And on Crete, you can buy almost anything. There's a in the south of Crete, there's a village with a functioning German tank from the Second World War. It still works, right? They're driving it around the village, and everybody, I mean, people in those areas all have AK-47s and shooting into the air, and at weddings, and it's a bit wild. This place, a little bit wild, and you can buy almost anything. So, hey, let's buy a crocodile. Okay, buy a crocodile. And you feed it, some scraps of meat. And then after a while, this crocodile gets bigger and bigger, and those things don't stop growing. And the owner said, well, you know what, I can't feed it any more chicken, so let's let it go. And it was walking around the island. And this was quite a thing, because we don't generally have crocodiles walking around the island. And it kept on growing for a while. It eventually died in the cold winter months, because it does get, I shouldn't tell Russians it gets cold. It gets a little bit chilly, put it that way. Up in the mountains, you will get to negative values, and the lakes wouldn't freeze over, but it just died. So so we want to move between positions from one place to another. We want to go from 0, 0 to 5, 5. And we can see down here, so we want to move in a straight line from 0, 0 to 5, 5. That is good, right? We don't want to ever get to the situation where we see an intermediate state and we become crocodile food. That's bad. Crocodile food is bad. Not crocodile food is good, right? And this is the demo where we don't want to ever see a dirty position. The position must either be 0, 0 or 5, 5. Never 0, 5, or especially not 5, 0. Right? That's what we're trying to achieve. So let's have a look at position, and we'll run this. This is going to be a nice little test. We're running it concurrently with two threads which are moving around, and then I think we've got 4 threads which are finding out the distance from origin. Let's try it out.
I always used to think that Sisyphus swam over from Egypt, Heinz, but I guess it's a little bit far.
I was thinking about that whilst I was actually thinking about that whilst I was giving this telling the story, and Egypt is just across the water from us, but it is a bit of a swim. So I would say it's not the most likely scenario. The more likely scenario is that somebody bought him as a joke, and maybe even got him as a wedding present from someone, and and just kept on growing. It's like, hey, this is good. This keep the dogs away, right? And if it doesn't, well, that solves another problem of food. All right, so here we've got our position.
Another thing I was thinking about
and the position
with this code, I had a thought about this code when I was looking at it last night, in fact, and I saw lines 23 and 24 of this move method, where we're going to move our x position by delta x and our y position by delta y. And actually, we are moving into Cephas's home. We first move X, and we're in his swamp, and then we move Y. But we're wearing an invisibility cloak, because that's synchronized. So that when he tries to check if we're there using the distance of origin method, he can't see us.
Exactly.
And we have to make sure that the
Exactly
distance
right.
from origin is also synchronized. Otherwise, he's going to spot us.
That's right. So if for example we made these volatile, these two, and had moved by synchronized, then we would, and not have the synchronized, we would end up in the jaws of Cephas. Now, I thought, because you said that you love maths, that you'd be complaining about the maths.square root over here, Pythagoras, because you know that there's actually a method called math.hypotenuse that does exactly what we're seeing down here. That's what I was expecting.
But I like seeing multiplication.
Well, the interesting thing is that math.hypotenuse seems to be slower than math.square root. I think they pay more attention that it's completely correct, and have a whole bunch of edge cases they have to cover, and so it turns out that math.square root is actually faster. And in the original code I had, the hypotenuse ended up being the bottleneck. So I was doing all this concurrency stuff, but actually what's really slow was hypotenuse. So that's why we're not going to be hypotenuse, all end up in hypotenuse, all crocodiles.
And what we want to test is
so this is the original
synchronization. Yes.
Exactly. And we're going to run the StampedLock position, and initially it's going to be just with synchronized. So I've got 2 writers and 4 readers. I've got 6 cores all running at the same time. And you'll notice that I've got the distance from origin is like 4.4 million times. The move 1, move 2, and move 1, move 2 are each about the same. So all of them take about the same amount of time. And they're all happily spinning around and all taking about the same time. And the best value for synchronized was moved by 6.7 million times within 3 seconds, and distance of origin was 4.9 million times. And the worst values were a bit worse than that. Okay, so this was with plain old synchronized. Okay, so we'll put it into this class just so we can remember what all the various options were. This was with synchronized. We had this. If we don't have anything, like take away the synchronized, the answer will be incorrect and will be eaten by a crocodile, which is apparently not very pleasant. I've never tried it. And this is going to be no synchronization. That's going to be broken. I don't know if my test actually tests that, because I didn't try this before. So we'll see what happens. But it should be pretty quick. It should be quite fast. So without any nothing stopping us, you can see we're doing like hundreds of millions of distance from origins, and the moving is also very fast. But of course, we're being chomped up by crocodiles, which is not very pleasant. So even though this is fast, it's not a useful thing to do. Instead, we want to do this with the stamped lock. So we're going to say, first of all, private final stamped. Oh, sorry. The first thing we want to do is to do it with the re-entrant lock. So I'm going to do that one first. Private final re-entrant lock. Entrant lock. So this is going to take the place of synchronized. We're going to do it as re-entrant lock. So the move by will be with the lock, lock.lock, and the distance from origin will also be with the lock.lock. And of course, we could put the math.square root outside of the distance of the lock, and that might be quite good. All right. So if I run this code, we should see the cost of doing it with re-entrant lock versus synchronized. So let's do that with the re-entrant lock approach. And we'll run that code as well. And we'll see how fast that goes. Right. And you can see that the performance is better than synchronized. It's better than synchronized. It's a bit more code, better than synchronized, but of course it's a lot slower than not having any synchronization. But that should be obvious, right? That should be obvious that it should be slower. So this is good. And these are the best values and the worst values for the re-entrant lock. Now there's one more thing I want to try, which John and I didn't speak about before. And that is, what happens if you make them fair? Because you can make a re-entrant lock to be fair, which is going to be true. So let's try that out with a fair lock and run that out. John is sitting there going, why is Heinz going off script the whole time? And, well,
I love going off script.
Where's the fun in not going off script, right? Where's the fun in that? And look at the results. Look at the results. So making it fair makes it really, really bad, right? Like really, really terrible. Okay, so we don't want to go that way. But obviously what we could do, instead of doing it with the re-entrant lock, we could also use a re-entrant read-write lock. So we could say we make a read-write lock and make a re-entrant read-write lock not fair. So fairness will not a good idea. And then we can say by move, we can say lock.write lock.lock. And then secondly, we can say lock.read lock.unlock, like so. And sorry, .write lock.unlock. And similarly here we can say .read lock.lock. Come on. And then lastly, we can have lock.read lock.unlock, right? And so this is with the fair lock. I'm going to just copy that over, just so I remember what it was. So that was really, really bad. That's like the absolute worst. Fair re-entrant lock. You don't want to be fair. Don't try to be fair. It doesn't work. And so this is with the re-entrant read-write lock. And if you run the code with the re-entrant read-write lock, you should see some very interesting results, maybe not what you expect. And you can see that the performance is actually worse on the distance from origin than with the re-entrant lock. And you go, it's re-entrant read-write lock. I mean, I can read concurrently, but there's quite an overhead with re-entrant read-write lock. So using it for something we're only doing a couple of reads is not going to give you a great benefit. So that's not really going to help you at all. All right. So this is
this
with
experiment. We have different numbers of readers and writers, which are showing up at the top of the output. Would that make a difference for this re-entrant read-write lock? The balance of readers to writers?
Yeah, it actually can. There are some cases where you can have the readers being completely starved by having too many writers. It absolutely can happen. Now let's go to the stamped lock, and that's the one that we really want to try out. Equals new stamped lock, and we'll call this SL just to make it different, and we'll use that same idiom that I showed you, and it goes like this. We're going to say long stamp equals SL dot try optimistic read. Then we're going to read. Oh, so that's the wrong place. That's over here. There we go. Then we're going to, I'll do the move by in a moment. So the stamp, we're going to get the optimistic read. Then we're going to read the values. Let's call it current x equals x and current y equals y. Then we're going to say, if not sl.validate, I always do it as quickly as possible, if I can. If it's not true, I'm going to do sl.readLock, get a read lock, and then I'm going to read the values again. I'm going to say current x equals x, and current y equals y. And this is what I don't like about this one, is that you actually end up unlock read. You end up having to do the reading twice, and then in the end you're going to use that for the square root. So current x and current y x times current y times current y. So this is what the reading looks like, and the moving will simply have a long stamp equals SL dot write lock. Nothing really special about that. And then in the finally we're going to say finally SL dot unlock write on the stamp. Right. So this is with the stamped lock. That's the stamped lock, but with the Java 8 idiom. So that's what you'll find if you look at the source code, this comment for Java 8, you'll see that idiom there. And if you run that code, you should see slightly better results than with the other options. And look at that.
So this one makes me
move is quite fast.
This one makes me think of my story of the invisibility cloak again. So we're going to try to sneak past and only put on the cloak when he opens his eyes.
Yeah, exactly. If he opens his jaws, you like quickly put on the cloak. So, but you can see the result here. The distance of origin is really fast in comparison to the move. So this is really great values, and much better performance than the other options. Okay. Idiom is a bit more difficult, but it is a lot faster. So these are stamped lock Java 8 idiom with that. I mean, look at those values. This compared to the first one, which was sort of the best, was 5 million versus 150 million. That's 30 times faster. Not bad. All right. Now
So Heinz, we don't have any.
There's a new idiom in Java 11
work that we're doing here. Oh, sorry. I was going to say we're not doing any kind of I/O work in this code. It's just mathematics CPU bound. Is that good for optimistic reads, or is I/O bound better? Is there a difference? Would we use this anyway?
You can use it for both. I've seen it used for both. So it's not bound to one.
That's great.
All right, now look at this. This is now a new idiom for optimistic read. And is that we've got 3 paths through this code. The first path is where you call optimistic read. Optimistic read comes back as 0 because somebody else is busy writing. We then go and see that the stamp is 0. We continue retry holding lock, that jumps back to 4. That label clarity, you don't actually need a label, you could just say continue, and that would also go back to 4. But it's just there for clarity to show exactly what's going on. So we jump back there, we get the read lock. This time the stamp will not be 0. We then read the state into local variables, and then we validate the stamp. So the second time when if it starts as 0, we're going to immediately go to the read lock, and that's going to give you the stamp that's not 0. So the good thing about this idiom is that you are only reading in a single place. And that's the first path through. The second pass through is that the stamp is non-zero, so it's a valid optimistic read stamp. And we manage all the way to here to stay valid, in which case we end up being able to call the process method. If you've got a read lock, validate will always be true. So we don't have to retry then. But if we get a valid stamp, and in the meantime somebody writes, we'll simply jump back to retry holding lock, get the read lock, and continue. It's a bit of an obscure idiom, but I think it makes a lot of sense because you have a single place where you're doing the reading, not 2. The only thing I would change is to get rid of this if stamp equals 0, because the less time we spend between optimistic read and the validate, the better our chances that we'll actually win this race. So that's why I would do it like this. Now, I'm going to skip this refactoring because it doesn't actually make a difference in performance. And I want to look at the last part, which is var handles. And var handles were added to Java to remove the biggest temptation to use unsafe. It's as fast as unsafe, it just goes straight through. And the way to do it is to create a var handle inside our class to make it static final, and a private static final. You don't want to leak those things out of there. And then you can use methods as if you're using them with atomic references and so on. But and so if you wanted to do this if you want to use var handles in this case, var handles aren't able to change two fields atomically. So what we would have to do is to actually create an object that holds all the data together, and then replace that using a var handle. That's compare and set, which is your normal returning a Boolean, like we would have in Unsafe or in atomics. But there's also compare and exchange, which returns the found value. So I want to do the refactoring on that as well, and we'll compare that to what we had with the StampedLock. Let me just quickly put this up. This is the StampedLock results. And then the var handle starts with the old synchronized version. And what we want to do is, the first thing is to combine the fields into a single field, which we're going to update using var handle. It's going to be private double array, just to be nice and lazy. And it's going to be, the position is going to say this.xy equals new double array of x comma y, like so. And then the move by, what we'll do is we'll have a double array current comma next equals new double array. So I'm always going to make only one double array. I say do, we're going to say current equals xy, current 0 equals next 0 plus delta x, plus not equals, that'll be wrong, and delta y, 1 and 1. And now we try and set it, so now we need the var handle. So the var handle we're going to define at the bottom of the class, private static final var handle xy, and we'll initialize it inside of in an initializer block. We're going to say xy equals method handles dot lookup dot find var handle on the class position dot class with the name xy, and the type will be a double array dot class. And of course you could get an exception there. If an exception occurs, we're going to catch reflective operation exception. We're going to simply say throw new error of e, like so. And then inside here we can say do while xy.compare and set of this, comma, the current, comma, the next is false. We keep on trying. We're going to keep on trying until we are able to set it. And then the distance of origin, here we'll say double current equals xy. And if you want to do it that way, we need to make this also to be volatile. So we can see the most recent value. That's what John complained about before, pointed out before. And then we can say double x equals current 0. And I'm struggling here with the keys. Let me say comma y equals current 1, and then we end up with math.squared x squared plus y squared. All right. So this is the code for position with var handles. And what is it complaining about? We can make this maybe final. No, it can't be final because we've made it final that we can't change it with VarHandle. So IntelliJ, stop complaining for no reason. Come on now. Tage, get that sorted out. So VarHandle. Okay, now we'll push that. We'll see how that performs in comparison. And this is going to be the VarHandle position. And we saw the synchronize before. And this position is looks
Well, Heinz,
looks not too bad.
should
Hey, John?
VarHandle be in the same class? Does it have to be in the same class, that creation of the VarHandle? Can't we put it somewhere else into our VarHandle finder or something? Is this the best place for it?
Yeah. Well, you have to be careful because this allows you to give you like superpowers. You know, you can't change you can't change final fields, but you certainly can read fields. What they actually do for the striped 64 is they use var handles to read from thread itself. So you can do all sorts of things that you shouldn't be doing. And once you've made a var handle, there are no more security checks being taken. So you have to be very careful what you expose. Now, as you would expect, the distance of origin be fast once it's warmed up, and much faster than the other options. But there are other things but the moving is of course going to constructless objects, which will make things slower as well. Now I've got just a few things. If you look at the slides, there's also a compare and exchange you could use. This doesn't really make it faster for highly contended code, but other code might. So we are near the end. I saw Alexi's already showing his lovely face, his friendly face. So if you have any questions, ones that John hasn't asked yet, you're welcome to throw them at us. We've got one more minute to ask them. And don't forget to join our little morning session gym. That's a lot of fun.
Yeah. So
We had a nice comment from Ivan about math hypotenuse having a bug. So it's something we can look at later.
Oh, there we go. Maybe it does.
Okay. So, gentlemen, let's continue the session in the discussion zone. You can just ask some questions to our speakers and experts. You can follow them on Twitter, so you can see all the Twitter handles on the screen right now. Again, gentlemen, thank you very much for joining Joker this year. And I want, in the very end of the talk, I want to remind to all our attendees that they can push Zoom button just under the player and join our Zoom discussion with John, Heinz, and Sebastian. Thank you very much, gentlemen, for the talk, and stay tuned. Okay.
Thanks so much, Alexi.